So this section relies on the notes from Jeff Schenker at the Michigan University and the book of Peter Lacks. So what we do is, so let's start with, we consider a linear space, and the linear space X is equal to the bounded functions on some set S. For example, R to the N, a bounded interval of R. And so there is a natural order on B that is for two functions X and Y. You will say that X is less than Y if for all S in capital S, X of S is less than Y of S, right? So we say that Fx is non-negative if for all S, X of S is greater than 0, and the linear functional L defined on B is said to be positive if it satisfies L of Y non-negative for all Y non-negative. So in this setting, we have the following theorem. So if Y is a linear subspace of B, and if there is some Y node in capital Y, such that Y node is greater than 1, and if a positive linear functional L is defined on Y, then you can extend L to all of B in such a way that L is a positive linear functional. So, in fact, to prove theorem 6, we are going to consider a more general setting. So, and we will work with cones. So, what's a cone? What's a cone is that something like that. For example, in R2, this is a cone. If you, so this is, for example, 0 in R2, this is 2, and let's say you're looking here. If you take X here and Y here, and a positive combination of X, sorry, so yeah, of X and Y. So if you take Tx plus Sy with T and S non-negative, it will remain in the cone. So the cone is a subset that is stable by positive combination of X and Y. All right, so the definition is right here. And linear functional on X is said to be P positive if P of X is positive for all X belonging to P. So with this setting now, we have also a theorem. And the theorem is the following. So now we consider a cone on X, and we assume that the cone P has an interior point Y node. And so if Y is a subspace which contains Y node, and so we assume that there is a linear functional which is P intersection with Y positive. Then you can extend L to X, and L is now P positive. So the proof, again, so it's the title of the section, application of the Hahn-Banach theorem. So we are going to apply it. So we first need to define our P, our function P, like in the Banach theorem. So let's give a try. Let's try to define P of X for all X in capital X as this infimum here. So you look at the values of Ly. So Y belongs to capital Y, the subspace in X, and you are constrained to Y minus X belongs to P. All right. So you, for a given X, you look at the sets of the Y's such that these two conditions are satisfied, and you take the inf over L of Y. Okay. Well, this should be an empty set, right? Can we for all X find a Y such that Y minus X belongs to P and Y belongs to Y? Well, yes, the answer is yes. Why? We look at the Y node. So the Y node is an entry point of X. And so by definition, there exists a positive T such that Y node minus Tx belongs to P. That's right, because if T is small enough, we know that's true by definition of an entry point. Now, next, since P is a cone, you can multiply that by 1 divided by T, and it will remain in P. But now it's good because now I have this form, which is right here. So now, so for all X, you can choose a Y, which is written as Y node divided by T. And in this case, there exists such a T such that Y node divided by T minus X belongs to P. All right. All right. Okay, so next, P is a cone. So, okay, some parentheses are missing here. So if Y minus AX belongs to P, then you can multiply that. For the positive A, it will also belong to P. And conversely, if the right hand side is true, also the left hand side is. Okay, so now if I take okay, now I will look at the definition here of P of AX. So P of AX is by definition this thing. And all right, but as I said, if Y of minus AX belongs to P, so I can divide this quantity by A, because this is equivalent. So this set is the same that this one, right? Okay, this I don't need that. Yes, I don't need that. So now if I call y divided by a z, I found, so y divided by a equals z, so z equals a, I replace here, and y belongs to capital Y is the same, is equivalent to say that ay belongs to y, so I can choose z belongs to y, it's the same. And now a is a linear function, so I can take out the a, and now if I look at this quantity, this is exactly a p of x, right? So yeah, we got that p as defined above is positively invariant. Okay, now let us have a look at the subadditivity. So in order to look at the subadditivity, we choose x1, x2 belonging to our linear space, y1, y2 belonging to our subspace, and in such a way that yi minus xi for both I equals 1 or 2 belongs to P. Now, since P is a cone, if both y1 minus x1 and y2 minus x2 belong to P, so do the sum of these terms. And I can regroup it like that. It's the same. But now, this is interesting. Why? Because now, if I look at the definition of P, which is this infimum here, this is the definition of this is the definition, right? But now I know that y1 plus y2 belongs to this set. Y1 plus y2 belongs to this set, so this quantity is less than this one. But now, yeah, and so by the linearity of L, I got that. So now, what can I do? As we already did, I can choose some sequences that instead I can choose here two sequences such that this one will converge as P of x1 and this one will converge as P of x2, and I will conserve here the inequality. So what I will obtain what I want, that is the subadditivity here. Okay. Okay, that's good. That's good. Now we need to prove that it remains to prove that L is less than P on Y. Okay, so let's do that now. So we consider X and Y, which belong to the subspace, and Y minus X belongs to P. So I can write L of X because X belongs to Y, and I write that L of X equals L of X minus Y. This belongs also to capital Y plus L of Y. Yeah, by linearity. So but then this is less than this because this is negative. Why is this negative? Because L of x minus y equals minus L of y minus x, and by definition, L is a positive linear function on the intersection of y and p. Okay, so and so this quantity is positive, but with the minus, it becomes non-positive. And so here it should be the y, the p enter y. Okay, so now from the definition of p, now the p is defined as an inf, and so from the is defined as an inf of L of y, and with this, so this works. So finally, we proved that. So we proved that L of x is less than P of x. Because L of x is less than L of y, and P is a infimum, so it's the so it's the so P is more than L, okay, by definition of P. All right, so now we apply the theorem of Hahn-Banach, and we can so we can extend it. We can extend L, and furthermore, we will have then L is less than P on the wall X. Okay, so but now we need to prove that L is a positive linear function on the wall cone, not only on the intersection of the cone and the subspace. So how we do that? Well, so how we do that? We choose x on P, x which belongs to P, and we remark that P of minus x is by definition this thing, right? But if you choose y equals 0, you obtain here x. So if y equals 0, y plus x belongs to P, because x belongs to P. So what you get? You get that P of minus x is less than L of y with y equals 0. So you get that P of minus x is less than 0. But we know that L is less than P from the Hahn-Banach theorem. And so L of minus x is less than P of minus x. And since L is linear, you get that L of x is positive as soon as x belongs to P. So we got our thing. So next, so now if you want to prove theorems, I won't give the details, it's just an application. of the theorem 7. And so you choose P as the cone of positive functions, and you can verify that y node, since the function y node is less than 1, it's an interior point in this. Okay, and so therefore you can apply theorem set, and this gives the result. All right, so I have to do some remark. So in the the definition that we used for interior points is the one we generally use when we define interior points when we have a metric. So for example, in the Banach space. But this definition, which works with balls, if you come back to the definition, so our epsilon is independent of y. So we could choose a more a weaker assumption as an interior point. We can make in the definition depend the epsilon of the y. Okay, and for example, so up to now, all the things work with either definition. What we did in the chapter, but there's a nice example on the reference of Schenker. So in this reference, so he extends. So you can. So the integral is a linear functional on, for example, the continuous functions defined on a bounded interval of R. All right. So for example, yeah, you choose 0, 1, and you have functions, and so you can consider the integral of f dx for f belonging to C of 0. So by the use of theorem 6, you can extend the integral, so the Riemann integral, to the set of just the bounded functions. So that's a nice result. But to do that, you need to say that y node is an interior point, and you need their definition. So if you want to do that, you need their definition, and so yeah. So that's a nice example. So I refer to you to these two references here that I have already mentioned. So that's it for today. So see you for the next lecture.